Okay, Assalamualaikum and a very good day everyone. So today we will be looking at chapter 4, which is copolymers. Now copolymers is a polymer that is made up of two or more monomer species. We have looked into this term actually in chapter 1 where you have homopolymers and copolymers. If you have homopolymer, then it will just involve one type of monomer species. But in the case of copolymers, usually we will make or we will introduce two different kinds of monomer species just to enhance the property or to get the required properties of polymer. And in fact, in industry, many commercially available polymers are made of copolymers. For example, you have PVAR, polyethylene vinyl acetate. So it will involve polyethylenes or ethylene monomers and vinyl acetate monomers. You will introduce different kind of functional group in the final polymers. We have the famous one, acrylonitrile butadiene in styrene, where you have the acrylonitrile as the monomers, and then you have butadiene. We have styrene as well. So it involves more than two actually. This is three monomer species to get ABS copolymers. So it will enhance the property by introducing the styrene bulky group, and then we have the cyanide functional group, and we have butadiene, which is the flexible chain polymer backbone there. In fact, the synthetic rubber or nitrile rubber is also something that we incorporate isoprene with a nitrile group. The process in which a copolymer is formed from multiple species of monomer, we call it as copolymerization. Copolymers is the name and copolymerization will be the process name. It is often used to improve or modify certain properties of plastic, because if you can see styrene will be bulky, it will be rigid functional group. So the backbone of the chain, the backbone of the polymer will be rigid. If you introduce butadiene or methylene group, it will be flexible. So if you want to combine those properties like rigid, a bit rigid but still flexible, you have to combine those kind of functional group or different kind of monomer species. Now, copolymers offer several advantages over homopolymers. They can enhance the durability, flammability, chemical resistance, and lower their melting point and adjust their density. This improvement can be classified into chemical, physical, and mechanical properties, making copolymers highly versatile and valuable in various applications. So in this slide, we compare polypropylene homopolymers and polypropylene copolymers, highlighting their key properties and applications. So for polypropylene homopolymers, it has high strength to weight ratio and stiffer and even stronger than copolymers. Polypropylene homopolymers are known for their excellent strength to weight ratio, making them ideal for applications where strength and rigidity are really crucial. And then they have good chemical resistance and weldability. They exhibit strong resistance to various chemicals, making them suitable for containers and pipes used in chemical industries. Good processability. So the ease of processing polypropylene homopolymers allows for efficient manufacturing of the product. And good impact resistant, even despite being stiffer, they can absorb impact without breaking, suitable for automotive parts. Good stiffness, they have high stiffness of polypropylene homopolymers, and it makes them ideal for applications like plastic chairs and storage container. Food contact acceptable. Polypropylene homopolymers are safe for food contact, commonly used in packaging, food storage container, and also kitchenware. And it is also suitable for corrosion-resistant structures. And their resistance to corrosions make them suitable for application in harsh environments such as outdoor furniture and chemical storage tank. For polypropylene copolymers, a bit softer than homopolymers but better impact strength, and tougher and more durable than homopolymers itself. Polypropylene copolymers are slightly softer but offer superior toughness and durability, make them ideal for products that require high impact resistance. And then they have better stress, crack resistance and low temperature toughness. So this better stress crack resistance and even low temperature toughness, they excel in applications requiring resistance to stress cracking and can perform very well at lower temperature, such as in packaging material that need to be stored in freezer. And it is also high processability compared to homopolymer, and in fact, like homopolymers, copolymer also have high processability, even better, suitable for a wide range of manufacturing processes. High impact resistant, the superior impact resistant make them suitable for products like car bumpers, toys and household goods. High toughness of copolymers ensure they can withstand repeated stress and strain, making them ideal for medical devices like syringe and vial, and not preferable for food contact application. Unlike homopolymers, copolymers are generally not used for food contact due to potential concern with food safety standard. Now, we have a few types of copolymers. So copolymers can be categorized into four main types based on their arrangements of the monomers. So let's see one by one. Right. So the first one is random copolymers. So they are two different units randomly dispersed along the chain. So it is actually randomly distributed along the chain. The second one will be alternating copolymers. So the monomer units alternate in regular patterns along the chain. So you can see that the blue one and then the red one, and then it repeats the blue one and repeats again the red one with regular pattern. The third one will be block copolymers. So it is a one in which identical monomer units form blocks along the chain. So they will be clustered together with the same types of monomer before they change to the second type. So you can see that the black color will be block, the first one, and then they will attach to the red one. The red one will be clustered together as a block before they attach to the black color. And so on. Okay, you can see the difference between alternating and also block copolymers. And then the fourth one will be graft copolymer. So homopolymer side branches are grafted onto a homopolymer main chain composed of different monomers. So you have a black one, we call it as a main chain, main polymer backbone, and then we will be having the side branches. You can see the blue color of monomer will be propagate as a branch, yeah, grafted from this main chain. So understanding the compositions of polymers is really crucial as it influences their properties and applications. Here we delve into the chain end model, or we call it as terminal model, which help us to predict the behavior and the compositions of copolymers. So the compositions of a copolymer cannot be determined merely by knowing the homopolymerization rates of the two monomer or individual monomers. This is because the copolymerization itself involves complex interactions between different monomers. So what we have here is the assumption. So this model makes two primary assumptions. The first one is the reactivity of a monomer unit at the growing chain end is dependent only on the identity of the monomer unit at the end, at that growing chain end. So it will be dependent only on the identity of the monomer at the growing chain end. That is the first one. Okay, the second one is the reactivity is independent of the chain composition preceding the last monomer units. So whatever we have, the rest of the monomer chain, it is independent. We only focus on the identity at the chain end. And this means that the nature of the monomer unit at end of the growing chain dictates how the chain will continue to grow regardless of the monomer that make up the rest of the chain. Alright? And then the last one will be in the chain end model. All propagation reactions are considered irreversible. These simplifications allows for easier modeling of the polymerization process. So the chain end model explains how a monomer unit at the growing chain end reacts. It can either react more with its kind or with the other monomer. So how does a monomer repeats unit at the growing end chain tend to react more of its kind or with the other monomers? That is the question that we need to answer. So actually they have about 4 possible propagation we will discuss in the next slide. So there are 4 possible propagation reactions, each with a rate constant K11, K12, K21, K22. Actually, K11 stands for K11, K12, K21, K22. Yeah? This constant help determine the preference for homopolymerizations or cross propagation. So either it will react with its same kind, so M1 react with M1, so you will get a propagation and all the radical at the M1. This is homopolymerization basically. Even M2 will actually tends to react with its kind, which is M2, another M2. So we have K22. So this is what we call as homopolymerization or self-propagations. And we have another type which is cross propagation or crossover reactions, where if you have M1 it will react with other type of monomer which is M2. You will have a rate constant K12. And then we have M2 react with another monomer type which is M1, so you will have rate constant to 1. Yeah. Alright, the monomer reactivity ratio or R help predicts the copolymerization compositions. It indicates the tendency of monomer to copolymerize either with its own kind or either with its different kinds. So for example, we have R1 is equal to rate constant 1 over 1 2, or R2 is equal to K22 and divided by K21. So based on the value of the R1 or R2, we can classify the copolymerizations type as alternating or randoms, block, or another alternating which have different type of R1 R2 or the product R1 of R2. So we can classify it into a few types of copolymers. So we have the first case, which is alternating copolymerization. So it really depends on the R1. In the final test, you will be given this value of the R1 and R2. So you just need to get the product R1 of R2 with R2, the product of R1 and R2, you will determine the preference and the type of copolymerizations produced. So in the case of you have R1 is equal to 0 and R2 is also equal to 0, then the product of R1 and R2 will be 0. So the preference is each monomer prefers to react with the others. So that means if you have M1, it will react with M2 instead of M1 and M1. So this will make up a perfect alternating copolymerizations, since they have the tendency to react with the other type of monomer. But in the case of you have R1 is equal to 0, but R2 is almost or both close to 0, okay, or what we call that as at almost 0, yeah. So the product will be 0, okay, or you have R1 almost 0, R2 is 0, the product will be also 0. And in the case of both close to 0, then that product will also almost 0. So this will make a preference each monomer prefers to react with the others, which mean you have still the alternating, but it is not perfect alternating copolymerization as before. So you have perfect alternating copolymerization, and the second case is not perfect alternating copolymerization or copolymers. And in the case of R1 and R2 is almost 0. Both are almost 0 with the same value. For example, in the first case just now is 0.03 and 0.02. It is not the same but almost 0, right? But in the last case is both of the R1 and R2 get the same formula. For example, if you start with 0.02, so R2 is also 0.02, then the product will be almost 0. Then the preference is neither monomer or homopolymerized very well. So almost perfect alternating copolymerization. Still alternating, but almost perfect. Not really perfect as much as the first one. In case 2, we have random or ideal polymerization. If you have R1 is equal to 1, R2 is equal to 1, then the product will be 1. And preference is there is no preference. So it will be ideal random polymerization. So it will be just random. Either it want to react with M1 or M2. So it will be ideal random. Okay, but in the case of you have R1 more than 1, but R2 is less than 1, so either the same case, which is R1 is less than 1 or R2 more than 1, so this both case, one of the monomer is more reactive than the others. It depends. If R1 is more than 1, then M1 monomer 1 will be more in the polymer backbone. It will be more reactive, so it will be more, the composition will be more. But in the case of the second case, this one, R2 is more than 1, then we can expect that M2 will be more in the polymer backbone or polymer chain. So the monomer or monomer 2 will be more reactive. So you have to write preference. One of the monomer is more reactive than the others. For example, M1 is more reactive than M2, or M2 is more reactive than M1. But in the both cases, that will be random polymerization, random copolymerization, yeah, random copolymerization. And in the last case, if you have R1 and R2 almost the same, for example, the value will be 1 point something, 1 point or 0 0.8, 0 0.8, for example, then this one will be random, random copolymerization as well. But the compositions of the M1 and M2 is almost the same. Okay, this is the most interesting copolymerization, as it is quite different from the others. So we have block copolymerization in the third case. If you have R1 more than 1 and R2 is more than 1, it is quite different from random copolymerization just now, because in the random we have less than 1. Okay, 1 R will be less than 1. But in this block copolymerization case, both R1 and R2 will be more than 1. So the value will be 1.86 or maybe 5 or maybe 3 more than 1. So when we calculate the product, it will be more than 1, of course. And preference, each monomer prefers to react with others of its own kind. So prefers to react with the others of its own kind, which means they will form a block. So it will react with the same type first, and then it will go to the different type. So it will make a block. For example, M1 will react with another M1, react with another M1, react with another M1, and then this block of M1 will react with another M2, M2, N2, and M2. Okay, this will create block copolymerization. Right. With that being said, I guess this is the end of the lecture. You can test yourself by doing this exercise. We will be discussing this chapter in detail in the physical class. So after you do this exercise, we also will discuss this in the class later. So see you guys again. Thank you so much.